Hey everyone, if you've been enjoying my free math lessons on Prodigy Mathematics, I've got a great way you can support the channel and supercharge your learning. I've launched Martian Mathematics, a growing collection of problem sets, quizzes, and fully worked out solutions designed to complement my videos. These aren't just generic worksheets. Each set follows my lesson structure, reinforcing key concepts with carefully crafted problems and step-by-step solutions. Every purchase helps keep this channel running, so I can continue bringing you high-quality, free math education. Check out Martian Mathematics on Teachers Pay Teachers today. Your support makes all the difference. And don't forget to like and subscribe. Lecture 6, Implicit Differentiation. So what is implicit differentiation? Well, let me first show you what explicit differentiation is, okay? When you have an equation where y is explicitly stated, like this, right? And I ask you to find the derivative of y with respect to x. Since y is given explicitly, we can just differentiate this guy, right? We know the answer, of course, is 2x plus 0 if you want, right? But what would you do if instead you saw y minus 3 minus x squared equals 0? And I said, I want you to find the derivative of this with respect to y. You'd say, oh, no problem. I'm just going to first solve for y. And I can just simply move all of this to the right. There we go. We've got the same equation, the explicit equation we look for, right? That we did just a minute ago, yes? Yeah. So that's what you do. You first solve for y. Now you've got an explicit equation in y. You can just differentiate it. Why would we need anything else, right? Well, let me give you another equation. What's the derivative of y with respect to x for this guy? Well, all you have to do is solve for y, right? Well, good luck with that. It's possible you could, because it's fourth order and we can solve up to fourth order, but if this was fifth or sixth order in y, you got no chance, unless you got a lucky guess, I suppose. But you're definitely not, there's no general way to find solutions to higher order than 4. And even this one would be really tough, I think. I haven't actually tried it, so maybe I'm speaking out of turn here. But so this is why we need an alternative. Now, I'm not going to do this one right now, because I want to be able to show you implicit differentiation and show you that it works by doing it, solving explicitly for y, and verifying that it worked out. First, we need to talk about the difference between equality and identity. Okay, so if I were to write down x squared equals 4, and let's say sine squared of x plus cosine squared of x equals 1. You're like, okay, I got something in terms of x on the left and something, a constant on the right. I've got the same thing here, something in terms of x on the left, a constant on the right. Surely the equal sign means the same thing in both of these, right? You'd think, right? So let's do something. Let's take a derivative on both sides. So if I take a derivative on both sides of this, so I'm going to d over dx on this guy, what would we get? Well, we'd get 2x on the left, and we would get 0 on the right, because the derivative of a constant is 0. And so you're thinking, okay, well, what does that mean? Does that mean that x is equal to 0? Well, does that work in, say, this form here? If I say, okay, well, x is 0, plug it back into this. 0 squared is 0. 0 equals 4. Doesn't seem right, does it? Yeah. Up here, this is what we call an equality. Okay, and it's defined over only a subset of all the possible x values. Can you tell me what x values satisfy this equality?
You mean 2x equals 0?
Nope, the x squared equals 4.
2.
Or minus 2, right?
Yeah.
So 2 or minus 2 satisfy this equality. No other x values do.
Yes.
Over here, what x values satisfy this equality? Well, let's do the same thing we did before. Let's take a derivative, right, on that. So we'll take a derivative on this over here, right? What is the derivative of sine squared of x? Well, that's going to be 2 times the sine of x times the cosine of x, because we take the derivative of a sine. We're just using the chain rule here, right? Plus 2 times the cosine of x times the minus, got to put a minus sign there, sine of x. And derivative on the right-hand side, what is that? That's derivative of 1 is just 0. Well, what does this tell us? This says, I'll just move this term here to the other side of the equal sign, and I'm going to get 2 sine x cosine x equals 2 cosine x sine x, which is really just another way of saying that 1 equals 1. Yes?
Yeah.
Because you can divide by that, and it's just 1 equals 1. So we call this an identity. And we usually denote it when we're specifying it explicitly that it's an identity by writing an equal sign with 3 horizontal bars.
Yeah.
So this says that sine squared x plus cosine squared x is identically equal to 1 for all values of x. There's no value of x you could plug in there where that won't be the case. And if you want to try, you can, right? You may remember a simple trig table. So 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, sine of x, cosine of x. What is the sine of 0 degrees? 0. Cosine,
1.
the sine of 0 degrees is 1? No.
Sine of 0 degrees is 0.
The sine of 0 degrees is 0, exactly. Cosine of 0 degrees is 1. The sine of 30 degrees, do you remember how to fill this table in? It's going to be 1 over the 2, square root of 2 over 2, square root of 3 over 2, and then 1. Then here we'll have square root of 3 over 2, square root of 2 over 2, 1 over 2, and 0. So if we were to plug any pair of values for the same x, right, x has to be the same, into this expression, let's say we put in the first one, 0 degrees. Well, we'd get 0 squared plus 1 squared is 1. Now let's try this one here. We put in 30 degrees, we'd get 1/2 squared plus the square root of 3 over 2 squared. What's that equal to? Well, this becomes 1 over 4. This becomes 3 over 4, and that is equal to 4 over 4, which equals 1. You see? So as you can see, the difference between equality and identity is that an identity is true for all values of x. Now notice that the derivative worked, right?
Yeah.
The derivative of the left side was in fact equal to the derivative of the right side when we had an identity. It's not true for an equality. So we must assume, if we want to, how do we say this? To do implicit differentiation, right, we're going to have to make an assumption that a function exists as an identity. So best to see it by example. So let's say I wanted to differentiate x times y equals 1 with respect to y. I want to know what the derivative of y is with respect to x. So that's my goal, okay? Now I know I can solve for y. It's pretty easy to do. That's kind of why I chose this as an example, because we'll be able to look at it from 2 different ways. But let's pretend for now that we can't. So the first thing we have to do is assume that there exists a y that is identically equal to some function of x. Another way to say that is we assume that x times y is identically equal to 1. Now it's beyond what we can do here to really prove all of this stuff. I kind of motivated it by showing you an example where the left hand and the right hand side's derivatives are equal when it's an identity, but not when it's just a simple equality. So that's the motivation behind it. You could do a formal proof to prove that, but we're not going to do that here. So make that assumption. Now, what's step 2? Step 2 is to use the chain rule and differentiate this. Using the chain rule on this, what do? Well, we have a product, right? So we'll have to use the product rule. So we'll do, so d over dx of x times y is equal to x times the derivative of y, dy dx, plus y times the derivative of x is just 1, and so we'll just say put plus y here. That's the left-hand side, right? The right-hand side, the derivative of 1 is just 0, right? So we get x dy dx plus y equals 0. We can solve, and so that's step 3. Now that we've done that, step 3 is to solve for dy dx. dy dx equals minus y over x. And that, in fact, is the right answer for the derivative of y. Before I show you how to do it explicitly, or before we do it explicitly, because I know you know how to do it explicitly, let's talk about our solution here. Now, can I put in, it looks like I could just plug in any old values for y and x here, and that would work. So I can say, okay, dy dx, let's say y is 3 and x is 2. Is that valid? I mean, it would give me a slope of minus 3/2, right? If y was 3 and x was 2. Yes?
Yes.
But does it satisfy this? Is 3 times 2 identically equal to 1?
No.
No, it's not. That's right. So you always have to check that the values for y and x that you plug in here satisfy the identity relationship that you assumed at the start. Okay? That's important. So let's look at how we would do this explicitly. We'll just do it over here to the side. So we can easily solve for y, right, just by simply dividing by x. We get y is equal to 1 over x, which I'm going to write as x to the minus 1. Yes?
Yeah.
And taking the derivative of this, we'll just use the power rule, right? So dy dx of x to the minus 1 is just equal to minus 1 times x to the minus 2, which is minus 1 over x squared.
Yeah.
But wait a minute. That doesn't look the same as this, does it? It does not. So what's missing here, I wonder? Well, I'm going to rewrite this as minus 1 over x times 1 over x. See that? It's the same thing. That's minus 1 over x squared, yes?
Yeah.
But notice that 1 over x is just y.
Yeah.
So I can rewrite this as minus y over x. Now does it look the same? Yes, it does. They're exactly the same. So let me give you one to try. So I want you to find the derivative of y with respect to x using implicit differentiation for this. So pause the video, try it now, return when you've got your answer. Okay, so step one, of course, is to assume that x squared plus y squared is identically equal to 1. So you might recognize this as the equation for a circle. It defines a set of points, x and y, right, which are identically, whose distance from the origin is equal to 1. Let's now differentiate using the chain rule. So the derivative of the right-hand side is just take the derivative, it's 0. Now I'm going to take the derivative of the left-hand side. I'm going to get 2x plus 2y dy dx using the chain rule. Now I'm going to solve for dy dx. dy dx will be equal to, we'll have the minus 2x over here, but we're going to divide out the 2, and so we'll have minus x over y. Minus x over y. And so if I choose points that satisfy the identity, that will give me the value of the derivative at that point, or at those, at that point.
Yeah.
So for example, again, this is a circle. And so if I pick, say, this point here, what is that point? Well, that's y equals 1, x equals 0, right? What do you think the slope of the line is here, right? Because we can put a tangent line up there at the top of that circle, and we expect to see a horizontal tangent line, yes?
Yeah.
So, and that's at the point 0, 1. So 0 squared plus 1 squared does in fact equal 1. So it is a point on this curve. The derivative at that point would be minus 0 divided by 1, which is just 0, which is what we anticipated, yes?
Yeah.
What about at the point here, at the point 1, 0? What do we expect the derivative to be there? Well, what does it look like? Let's draw it in. Let's draw the tangent line to that point. That looks like a vertical line, right? Is the slope of a vertical line defined? No, it is not. So the derivative does not exist at the point 1, 0. And you see what happens when we try to plug in here. I mean, 1, 0 works in the identity. 1 squared plus 0 squared is in fact equal to 1. But the slope at that point would be minus 1 over 0, and we can't divide by 0. So it is undefined. The derivative does not exist at that point because it has a vertical tangent line, okay? Now, we could have done this explicitly. Remember, the first thing you assume is that there exists a function, y, that is identically equal, that is defined identically. Y is identically equal to some function f of x. Functions are single valued, right?
Yeah.
For any x, you only have one and only one possible y value. But let's explicitly take the derivative of y. So we would solve for y. That would give us that y squared is equal to 1 minus x squared. And so we can just take the square root of that. But remember, it'll be plus or minus the square root of that, yes? So to explicitly solve for y, we'll get a multi-valued equation, right? There's no f of x which can be multi-valued. Okay, there's no function that is multi-valued. So what we have to do instead is we could say that y is identically equal to, call it f1. All right, let's just do f of x, which is equal to the positive 1 minus x squared. And then y is also identically equal to a g of x, which is equal to the negative 1 minus x squared. You have to create two functions. Now, of course, when we implicitly took the derivative, that would work for both of these, okay?
Okay.
If we do it explicitly, we're going to have to take these one at a time. Because we're going to take the derivative. We can't take the derivative of this, but we can take the derivative of this or the derivative of this, okay? But when we did it implicitly, we didn't have to worry about that. So it seems to handle multi-valued equations quite easily. So in your homework in the past sections, you've been applying the power rule to problems like this, haven't you? If I had like y equals x to the 1/2, you've been using the power rule to find the derivative of that, right? So you'd say, well, that means that y prime is equal to 1/2 times x to the 1/2 minus 1, or 2 over 2, which gives me 1 over 2 square root of x. We've been doing that?
Yes.
Yeah. Well, we shouldn't have been doing that technically, because we proved the power rule for integer exponents. We didn't actually prove it for rational exponents, and so we're going to do that now. At least we're going to try to. So if y is equal to x to the p over q, let's first raise y to the q power. So we get y to the q is equal to x to the p. By doing this, we now have the equation in a form that we can use our regular power rule on, plus using implicit differentiation. So we first assume this is identically true. Take derivatives on both sides using the usual power rule. We'll get q times y to the q minus 1. But this is a chain rule, so we'll get dy dx. This will be equal to p times x to the p minus 1, just using the usual power rule. So let me divide both sides by qy to the q minus 1. Gives me dy dx equals p over q. And we'll get x to the p minus 1 divided by y to the q minus 1. Now at this point, I want to make a few changes here. So this is equal to p over q of x to the p over x, because x to the minus 1 is just x, or 1 over x, right? And this will give me y over y to the q, similarly, for the denominator here. Now I'm going to use this relationship here and this relationship here to substitute in. So what do we get? P over q, x to the p divided by x times, well, for y is x to the p over q, so I get x to the p over q, yeah, for y. And then for y, substituting in for y to the q power in the denominator, I'm going to get x to the p, like that. Yeah, looks good. So you see that this cancels this. Get the p over q. The x to the p over q divided by x is the same thing as x to the p over q minus 1, because 1 over x is the same thing as x to the minus 1, adding exponents in the usual way algebraically, and we have our result. This is the power rule for rational exponents, and we were able to show that using implicit differentiation. So let me give you one to try at home. Tangent of x times y equals x squared plus y squared. Yeah. So using implicit differentiation, pause the video, solve that at home, come back when you've got your answer. So again, first thing to do is to assume this is identically equal to x squared plus y squared, and then proceed differentiating the left and the right-hand side. So we'll do the left-hand side first. The derivative of the tangent of something is, of course, the secant squared. You do 1 minus the tangent squared, but we're going to do the secant squared. I think it makes it a little easier. The secant squared of x times y. And then the chain rule, of course, we have to differentiate the inside, but that is a product. So we'll have y times the derivative of x is just 1, plus x times the derivative of y is dy dx And that takes care of things for the left-hand side. I think we'll want to pull this dy dx out so we can do something like this. Secant squared of xy times y, I'll put the y in front, plus, we'll say, x secant squared of xy dy dx. Yeah. And on the right-hand side, we're going to get 2x plus 2y dy dx. Setting the left-hand side equal to the right-hand side, which we can do because of this assumption that these are identically equal. We're going to collect dy dx terms. So we'll have we'll get x secant squared xy dy dx minus, because this is on the right-hand side, minus 2y dy dx equals, this is still on the right-hand side, so we keep that as 2x, but we have to move this to the left hand, the right-hand side. It was on the left. Y secant squared of xy. Now all we have to do is factor out dy dx out of this. Parentheses around that. Dy dx. And we'll divide both sides of the equation by this term here. So we'll get that dy dx is equal to 2x minus y secant squared of x times y divided by x secant squared of x times y minus 2 times y. Not pretty, but it's something you can work with anyways, and you do have an explicit form for the derivative of y with respect to x. In the chain rule lecture, we did talk about related rate problems, and I want to show you why implicit differentiation can be of real benefit by looking at a related rate problem. So you're probably familiar from physics with the idea of parallel resistors, right? That if I put two resistors in parallel, R1, R2, where the electrical current will flow through both paths, right, R1 and R2, that the rule for adding these two up to get an equivalent resistance is like this. 1 over R EQ for equivalent is equal to 1 over R1 plus 1 over R2. Now you can, of course, solve for the equivalent, for R equivalent, and you would get R equivalent is equal to R1 times R2 divided by R1 plus R2. And so if I wanted to, let's say I was doing a problem where I had these two resistors could vary in time, so I could, change the resistances, right? I think they call those rheostats? I think they're called rheostats. They're variable resistors. You can imagine making one by simply having a long wire that is connected electrically on the left, and then a moving point connected on the right. So you go through either more or less wire, increasing or decreasing the resistance, you see? So if I know what the rate of change of R1 and R2 is, so if I know dR1 dt is equal to some constant, some value rather, I'll call it A maybe, and dR2 dt, some other value B, then the question is, well, how does the equivalent resistance change as a function of time? Because that's all that really matters to me in my electronic circuit. Don't care what's going on in the individual resistors. I want to know about the equivalent resistance. That's what affects the, the total behavior of the circuit. So we can use implicit differentiation to figure this out, because doing it this way, you've got a quotient rule problem with a product rule in the built in part of it. So it looks like it's going to be messy and a lot of algebra. But let's see if implicit differentiation isn't easier to crack, and we can work with this equation here, which is typically defined in terms of what they call the conductance, right? Where 1 over the resistance is the conductance. So let's use this and see if we can't figure out what dReq dt is. So again, this is a related rate because both R1 and R2 are changing with respect to time, just like the the balloon problem from the last problem set in the chain rule. I'll put a bunch of problems of this nature in the problem set for this lecture, just to get more practice at it, because they're very useful. I was going to showcase an economics problem, but I think it would take too long to explain, so I'll just put that in the homework instead. So let's have a look. So first we have to assume that there exists a function REQ that I can, that's EQ, not EF. That this is identically equal. All right, so we're going to use the chain rule on the left-hand side here. And so on the left-hand side, we'll get the derivative with respect to time of, I'm going to write it like this, REQ to the minus 1. Well, what's that equal to? That's going to be minus 1 over REQ squared times DREQ dt. So that's the left-hand side. On the right-hand side, the derivative with respect to time of 1 over R1 plus 1 over R2, where R1 and R2 are both a function of time, remember, right? So what's that equal to? That's going to be minus 1 over R1 squared times dR1 dt minus 1 over R2 squared dR2 dt. And I think at this point in time, I'm going to employ the very common technique of replacing this time derivative with REQ with a dot above it. In physics, you see this a lot. Time derivatives usually mean, the dots usually mean that it's a time derivative, so we would write it like this, REQ with a dot above it. See that? That means the time derivative. So I can also replace these terms here, dR1 dt, with just R1 dot, and dR2 dt I can replace with R2 dot. Makes it a little bit neater, I think. So left and right hand side are equal because of a theorem that we did not prove, but we kind of motivated, that the derivatives of identities, the left hand side and the right hand side, the derivatives are equal. And so we can, of course, equate these two and solve for REQ dot. So that would mean multiplying by minus. Do you want to multiply minus? Well, we'll distribute the minus all the way through. So that'd be REQ squared, that's from here, times R1 dot over R1 squared plus R2 dot over R2 squared. Yeah, that looks good. Yeah, and you could, if you wanted to at this point, right? I know it seems like, well, if I solve for the equivalent resistance and then I plug it into this, what's the purpose of doing the implicit differentiation? Well, I get to avoid having to do a quotient rule and a product rule combined together. This would be a lot of algebra. You're likely to make a mistake with it. This is not very much algebra at all, right? Very simple derivatives. There's not much involved there. So what I want to do now is substitute in for R equivalent using the explicit formula for it. So if I do that, I get that, and this time I'm going to write it out as dREQ over dt, because that's what we were looking for in the first place, is equal to, and I just square this, right? It's going to be R1 squared, R2 squared over the quantity R1 plus R2 squared times R1 dot over R1 squared plus R2 dot over R2 squared. And here you can use, for R1 dot, you would use this constant A for the rate of change of the first resistor. And for R2 dot, you would use this constant B that we had specified there at the beginning. So that's typical for a related rates problem, where you give it an actual number for a rate and you substitute it in to get a value, okay? But the point is that I got to avoid the ugly differentiation of the quotient rule combined with the product rule by doing this implicitly. So it's got a lot of value, a lot of utility. Now, at the beginning of the lecture, we had an ugly equation that we knew we probably could not solve explicitly for, and we want to see now how we can use our technique of implicit differentiation to find the derivative of y with respect to x. So here's the equation we started with. X to the fourth plus xy cubed plus y cubed equals 3. And we would like to find, say, the slope of the tangent line when... Can anyone see a solution to this equation, by the way? 1, 1, right? So if x is 1, y is 1, 1 plus 1 plus 1 is 3. So we want to find the slope of the tangent line, so m at the point 1, 1. But to do that, of course, we need an equation for the slope of the tangent line. That would be the derivative of y with respect to x. So we will assume this is equal identically and proceed to differentiate both the left and the right-hand side using the chain rule and the product rule. So starting on the left, so left-hand side, what do we get? We get 4x cubed Now we have to apply the product rule across this. So we get y cubed times the derivative of x is just 1 plus x times y cubed would be 3xy squared times dy dx. Plus, through differentiating y cubed, we'll get 3y squared dy dx. That's the left-hand side. The right-hand side, of course, is just equal to 0 because the derivative of constant is 0. So setting these two equal to each other, left-hand side equals right-hand side, and factoring out dy dx, we'll get that dy dx equals all of this with a negative sign in front of it, minus 4x cubed plus y cubed, divided by these two terms, missing the dy dx, of course. So we'll get 3 times xy squared plus y squared. Yeah, it looks right. So we can now substitute in the points 1, 1, which satisfy our identity, as we've already discussed, into this equation to find the slope of the tangent line. And that would be we get 4 plus 1 over 3 times 1 plus 1. That's going to be minus 5 over 6. Okay, and again, if you were to look at the graph of this, right, it doesn't really look like a circle, but it's kind of circle-like, okay? It has a bit of a skew to it because of the cubic terms in here. And at the point 1, 1, that's somewhere over here, right? We're going to get a tangent line which should have a negative slope to it, and we see that it does here. And so in the video, I'll post an image of this equation graphed and that tangent line added so we can see that. I did not give a lot of in-class problems for you to try while you're watching the lecture, but there's plenty of opportunity for that in the homework. So I think next time we're going to talk about sketching equations using the tools of calculus versus graphing equations like you would do in algebra, or plotting rather. Right? In algebra, you plot equations. Yes? You make a table of x values, you plug it into the equation to get the y values, and then you plot those points, and then you interpolate by drawing lines between the points, right? So in the next lecture, we're going to look at how calculus can be used to sketch graphs rather than simply plotting them. So I'll see you then.